All right, so let me try to explain how this addressable LEDs communicate and what the timing requirements are. So the um, we're going to be using the Raspberry Pi Pico. So I have everything connected here, ready to go. Don't mind this one, this is for another project. But I have my LEDs right here. I have my oscilloscope connected to the signal line so we can see what is being sent, or at least the square wave that we're going to be sending. And we will be able to see the signal on the oscilloscope right there when we send it. The signal is connected to GP16 of the Pico, so that should be easy to follow. It's not going to be a lot of code, it's just going to be a lot of talking, a lot of explaining. So in the data sheet, uh, this is just a section of the data sheet, but it's the most important one. So in the data sheet for the addressable LEDs, it says that each LED requires 3 bytes for the full color spectrum of what they can handle, and each byte is 8 bits. So the color can range from 0 to 255. One for green, for red, and for blue. So you can combine all of those three, and they will give you I don't know what the range of, but it's a big range of colors that you can do. So the requirements are, we need to be able to send a full byte of color, 3 bytes per LED, and this section here of the data sheet is showing us the timing requirements to send a single bit of data. So it's telling us how to send a 0 and how to send a 1. So let's figure out how to send a 0 first, right? So this is a square wave signal, and it's telling us that it requires a high side and a low side with some timing parameters. So for the high side, for the 0, TH0 here, it says that we need 0.35 microseconds or 250 nanoseconds, plus or minus 150 nanoseconds. So for the high signal, we always want to shoot for the low range, so we can send as much data as possible the fastest we can. And for this one, also somewhere at the low range, but this is the transition before it goes into the next one. So we have a lot to play with this, not so much with this. So how do we come up with this time? So how do we make sure that we can accomplish this timing parameters? Well, you have to consider your MCU. So in this case, the Pico is running at 133 megahertz. So 133 million cycles per second, or it's 133 cycles per microsecond. So if we divide 1 microsecond into 133, we get 7.5188 nanoseconds per cycle, right? So we have that. We can calculate what it's going to take to accomplish these times. But first, let's see if it's really running at 133 nanoseconds, 133 megahertz. So if it is, and each cycle takes 7.18 nanoseconds, that means that if we toggle an LED from the time it goes up to the time that it goes down, we should have about 15 nanoseconds in between those two. So let's do that and measure it. So GPIO, we said we're going to use 16. Set direction as an output, and then we'll toggle 16 to on and 16 to off, and it's just going to loop and do that all day. All right, so let's compile this, and let's enable the oscilloscope, also the camera at the bottom. All right, so did it compile? Yeah. All right, so it did compile. So reset this, and I'll send it over. And there's the signal on the oscilloscope. So let's measure that and see what we have. All right, so there's the signal, and let me try to align it. So this blue lines here, there's the blue line here and a blue line there, vertical line, and that's gonna give us the measurements right here, where it says 30 nanoseconds. So let's go and look at where it comes down. So right around there, right? So it says 15.2 nanoseconds. It's hard to tell when it starts going up and when it starts going down. So that's accurate. That's 133 megahertz. The clock is running. So now that we can set a signal to go up and to come down, we just need to put a gap in between, right? So we have this thing. Let me hide this thing. So we took care of this line going up and coming down. So now we just need to extend the time here. So we need 350 nanoseconds plus or minus 150. So we're just going to go minus 100. So that will give us 250 nanoseconds. So to do 250 nanoseconds, 250 divided into the time it takes for one clock cycle, which is 7.5 nanoseconds. It says we require 33 clock cycles to accomplish 250 nanoseconds. So I'm going to use a little bit of assembly instead of the PIO just to make it easier to understand. That way it will be very little code, but the result will be the same. All right, so this thing, I'm just saying that, you know, don't optimize the code because what I'm going to write is what I want. I want those clock cycles. So I'm going to use the this instruction to repeat the next instruction whatever number of times I want. So it says 33 here, so I'm going to put 33. And the instruction I want to repeat is NOP, or no operation, which means that it's not going to do anything, but it's going to waste a clock cycle. Right? And once I'm done with it, I'm going to say end of repetition. And that's the end of it. So this is just the gap that we're going to put. So this is going to be this gap right here. So it says 33, right? So I put 33 here, but in reality, if you consider everything that is going on here, we know this takes a clock cycle. I know this is going to take a clock cycle. This is going to take a clock cycle, and this is going to take a clock cycle. So we have 1, 2, 3, 4 extra clock cycles that we need to account for. So this really should be 29. Right? So let's compile this and see if that's what's going to happen. We'll see it on the oscilloscope and see if it makes sense. All right, so there you have it. The signal got way bigger. All right, so let me move it to the blue line. So that says right there, so here's the vertical lines. It's 244 clock cycles. So, you know, obviously the signal is hard to measure because it's at the nanosecond level. We need to expand it even more to be able to get it very accurate, but I'm sure it's about 250. It reads 244, close enough. It's above 200 and way below the maximum. So now the next step would be to expand this part, right? Because we took care of this, now we need to take care of that other one. So for that one, the TL0, which is this right here, says we need 800 nanoseconds plus or minus 150. So we're gonna shoot for 650, which is at the limit, right? But in the timing in between where it does other stuff, we should be fine. There shouldn't be any issues. So we're just gonna copy this. So this is the high pulse, and this is gonna be the low end. So let's calculate for. So it's 800 minus 150 will give us 650. So we want to accomplish that those 650 nanosecond delays. So it's going to be 650 divided into the time it takes to do a clock cycle. And it says it's 86, right? So it's 86, and like we said before, this takes a few clock cycles extra, right? So this is one. We still have, I know we're accounting for this one up here, but we also need to account it for down here. So 1, 2, and 3 clock cycles. So instead of 86, we're going to use 83. And that should give us roughly what we're looking for here. So let's compile this. So that's the signal we have. We're going to expand this gap right here. We got this one. We need to get this one. All right, so let me reset this thing. Now this light now is coming on because we are sending a valid signal, but it's just continuously, so it's all bright, but that's not what we want. We're still trying to tune the signal. So there's the signal. Looks much better, right? So now let's measure the gap. So that's one vertical line on the left. And let's move the other one here. And that says 720, which is more than what we need, right? And it's not 700. The reason it's 720 is because we're measuring from here coming back around to here. So there's a delay for the return, and then there's a delay, well, there's clock cycles for the return, and then there's clock cycles for the checking to see if it's still 1. So there's about 3 clock cycles here before it lands into this, and then an additional clock cycle for this one. So 4 total clock cycles. That's why we're seeing 720, right? So I guess what we can do to verify that that is the case, we can just add this twice here, and we'll set it to 1 and 0, so we can identify exactly where this thing ends. We're almost done. Let me send them over. So now you can see that little pulse right there. Those are the 2 lines we did. So that's the real measurement there. So the measurement is up to here. It says 664 nanoseconds. And if we want to measure how long it takes for the loop to go around from the bracket at the bottom, so it says it's about 50 nanoseconds. So it says that from here to here is 50 nanoseconds, right? So 50 divided into 7 point, or the time it takes for a clock cycle. So that's 6 nanoseconds, right? So there's 1 here, 2, 3, 4, 5, and then we're missing a 6 at the last one. So who knows which one is taking? Maybe this one takes 2 clock cycles and this one takes 2 as well. And then we have this one and this one. In any case, we have the time we want, right? So now that we have the 0, we need to define the 1, but we don't need to keep doing this. We have something that works. We have the proper timing. We know how to calculate it. So we can go and create our functions now. So we'll just the first function will be named set color bit, and we're gonna set it if it's a 1. So if it's a 1, we already have the 0, right? And if it's a 0, I mean if it's a 0, so this is for the 0. If it's a 1, we need to calculate this part. So let me first format the document, right? So if it's a 1, since we already calculated the 0 and it's down here, if it's a 1, we're going to do this one. It's T1H, right? So we're going to do this. 700 nanoseconds plus or minus 150. So we're going to do 550. No, 600. So we'll do, so it's 700, plus or minus 150, but actually we're just going to go for safe at 100, right? So 600 nanoseconds divided into the time it takes to do a cycle. 79, and we already know that there's 4 extra clock cycles here, so we're gonna do 75, and that will give us a proper time. Now for the low part, T1L is 600 minus 150, so it would be 450, right? 600 minus 150, 450, and we divide that in the time that it takes to do a clock cycle, and it was going to give us 59. We're going to account for 3 clock cycles, 1, 2, and 3, so it will be 56, and that will give us the 1 and the 0. So that means, oh, let's see, I was referring to this one here, right? So we were first defining this one, T for the 1, so T1H right here, 700 minus 100, 600. That's what we have here, 75, right? We did the calculation. You guys did see the calculation. And then the second one, T1L, this one, 600 minus 150, 450. And then with the calculation, and we ended up with 56 to account for the 3 clock cycles. I know it's getting a little complicated. That's the end of the complexity. Now we can set some colors. So regardless of the software you use or the MCU, you're still gonna have to come up with this timing parameters, and it will work. If either you do it like this, do it with a regular for loop or a while loop, or you use DMA or PIO, it's all the same thing. It's the timing, right? That's all it is. Which means you need to have a processor fast enough that you can split it into these times. It will, you won't be able to control it accurately at 8 megahertz, but at 16 and above it's pretty accurate. So let's test this part, right? So we're gonna send a color. So actually that's not what we want. We want more control over this. It's a single bit. So let's create another function. This is going to be color byte. So the other one was bit. And let's call it color. And we're going to send 1 bit at a time of the color value. Right? So we just need to send this a bunch of times. Don't know if those are the 8, but we'll see. So 6, 7, and 7, 6, 5, 4, 3, 2, 1, and 0. Okay, so this will allow us to send 1 full byte, and this function will call each individual bit and set them accordingly. So we set that to set an LED, we need to send 3 bytes. So let's send something that is not too bright, so 30, and 0, and 0. And I believe this is green, the first color. So we're gonna set it to green, and we're setting the red to off pretty much, or black, and then the blue to black as well. So we're gonna have a single LED, the bottom one, and it's gonna turn green. Not very strong, so you guys can see it. So let me compile, and let me enable the camera. Move it. Oh, did it compile? Yeah. Right. Oh, it already turned green. Not sure why, but let's move it over. It's too bright though. That's not the right color. All right, there it is. Can you see it? Yeah, you can see it. Not sure if it's working. Let's see. Let me put it lighter. I don't know if that's the right green. Let me move it once again. Yeah, they all turn green. All right. So the reason this is happening is because we're also missing this section here. So this is the, I'm not sure what retry. I'm guessing this is where you say this is the end of communication and light them up, and then I'll send you a new batch of colors. So it needs to be a low of about 50 microseconds. So we'll put a 50 microsecond delay because when we send a color, the last one is set to low. So we don't have to set it, it's already low. We just need a delay. Right, so let's put 50. Let's compile it, and this time let's put 30. So it will be bright, but not too bright. Right. Let me reset this. So they're all green because it was just looping too fast sending colors. So now when I send it, only the bottom one should have a color green, not too bright. Alright. It didn't reset the other ones though. That's okay. So let me reset the whole thing. So there's your green, and then we'll do the other ones as well. Right, so there's the green. Now let's change the other one to red, and then the last one to blue. So now that we have this, we know how to change the colors. So we'll do all three, and then that will be, so this will be green, this one will be red, let's set 30, and then this one will be blue. So notice that I'm setting the first byte, which is the green, and then on this one I'm setting the second byte, this one, which is the red, and then on this one, last one, I'm setting blue. So let's compile that part. Let me reset this. Send it over. And there you should be able to see those colors. Right, so where they are. And you know, obviously if I want them all blue, now what you do with this code is up to you. If you want to put some logic to blink it or do some random stuff, you know, let's say we want the bottom one to, I don't know what that color will give us, I don't know what this color will give us, I don't know my color combinations, but now I have the first 2 bytes, which will be a combination of green and red. It will give us a color, and then we have red and blue, and it will give us another color. And then on this one, on this last one, we'll just leave it as red as well. So the bottom one is going to be red. No, the last the last. So this is the first LED, second, third. So the last one will be red, and then the two at the bottom are going to have different color combinations. Let's see what we get. There we go. Look at that. Let me make this big. All right, so those are the colors. And again, you know, I'll just go and set the red, white, and blue, I guess. So white and blue. And there. I don't know if you can tell, there's red, white, and blue, but I can see pretty clearly red, white, and blue. I don't know if the camera can pick it up. And I just noticed that I didn't show the color. I mean the the code itself. So there's the red, the white, all of them are lit up. Not very strong, but they're all lit up. And then the blue here is lit up. We have a delay of 50 milliseconds, which is too much, right? Because it's saying it's 50 microseconds, not 50 milliseconds. So you can send a lot of data very quickly. So let's just recap before I sign off. So you know, this is probably the complicated part. So just focus on this. So we're sending a bit of data, right? So it's telling us how to send a bit of 0 or a bit of 1. And T0H, which is right here, is telling us these are the timing parameters for the pulse for 0, which is 350 nanoseconds plus or minus 150. I believe we're doing 250 with this because each of the clock cycles at 133 megahertz takes 7.5188 nanoseconds. So if you account for this plus the 70 plus this one plus the 70 times this thing is going to run, and then this one and this one, that will give us 250 or very close to it, right? And then second, we have this other one again, which looks identical except for the number here. That's to extend this part. So all it's saying is this instruction is saying execute 56 times the next block until you find this one, right? So this thing is going to execute 56 times, and this thing doesn't do anything. It's just a wasted clock cycle, if you will. So it's just going to sit idle doing nothing for 56 clock cycles. So that's if, actually this is if you get a 1, right? So it would be this signal here. We have here, if it's a 1, right? If what we're sending is a 1, then we do this pulse or this square wave. If we send a 1, it's this one down here. Sorry, if we send a 0, it's this one here, which is the same as this with a different number of times that is going to repeat the no operations. Right? And then we have another function here that calls the one above, this one. And this one sends, it calls it 8 times. So 1, 2, all the way to 8, right? And it calls it with the highest bit first, and then the second, third, fourth, all the way to the first bit. And it compares it against the color to see if it's a 1, it sends whatever number, otherwise it sends a 0. And then in the main function, we're enabling GPIO 16, which is where the signal is coming from. And then we set the direction as output. We get into an endless loop. And then we send 3 bytes of color for each of the LEDs. I have 3 LEDs. So this is for the first LED at the bottom, the middle one, and the top one. So we're sending red. So it's green, red, and blue. Those are the byte sequence. So we send red, and then we're sending all of them green, red, and blue lit up. So that makes a color white. And so we have red, white, and then the last one we're sending blue. Wait 50 milliseconds and do it again. So that's all it's doing. It's a pretty long video already, 27 minutes, but it's good to understand this timing requirement, so that way, regardless of what you use to control those LEDs, it will be easy to do, as long as you're able to do those timing parameters. All right, that's all I have. If you have any questions, you can look in the description, and I'll have a link where you can go and ask.